Welcome back from your delicious repasts, which I hope you were able to enjoy, and it's good to see you all here. And we're back for this afternoon's session. I hope you're enjoying this session. It's really fascinating, don't you think? I mean, really is. We've got probably, I think, this afternoon, in terms of IQ power, we probably have the best group ever assembled at Hudson Institute, except when Herman was on the podium alone. Anyway, we're going to talk about what's happening internationally. We've talked about the U.S. I think there's a general consensus the U.S. has been really in the lead, both in terms of private companies, but also in the federal government, and working its way through what we're calling the quantum race, moving forward. But it's also important to understand what's happening and what's taking place in the international arena as well. You all saw Sean Kwok's slide of the quantum race as it's taking place around the globe. I counted 21 countries total, and all of them investing sums of money, some of them really quite substantial, for their entry into the quantum race. And it seems like almost every time you turn on the newspaper, you see, notice I said turn on the newspaper. On your app, I mean, of course. I'm talking about the app. Come on. Give me a break here. You turn on your newspaper. It seems like another country has announced that it's entered the quantum race. There was Japan. There was India. I don't remember if India was on your map or not. And, of course, the Russians also have a keen interest on this, plus the Chinese. We've mentioned the enormous quantum research facility that they're building. They're putting some $10 to $12 billion into the construction of that site and the work that they're doing. Work, by the way, that the Chinese are unabashed about it having strong military applications, both in terms of providing additional stealth for Chinese submarine fleet, for decrypting possibilities, etc. They're very straightforward about the fact that they see this not just as pure research or a desire to reach a quantum computer as a goal in itself, but that it has profound national security and geopolitical consequences as well in who wins that quantum race. So we've got 4 panelists, 2 of whom we have heard from before, and then 2 additional new entries into our discussion about where quantum computing, where quantum research is going, and why it's going and headed in the direction that it is. We've got, in reverse order of presentation, we've got Martin Laforest, Senior Manager, Scientific Outreach, Institute for Quantum Computing. You remember him from the panel that he moderated on quantum computing this morning. We've got Dr. Jane Melia, Vice President of Strategic Business Development at QuintessenceLabs, again, one of the leading organizations working on this process. We're delighted to have Mr. René Copeland, President of Dwave Government, Inc. And we also have, again, a refugee from one of our morning panels. We have Dr. Christopher Monroe, Professor of Physics, University of Maryland, and Chief Scientist at IonQ, Inc. So what I'm hoping we'll be able to have is presentations from all 4 of them, and then that we'll have some time at the end to open up to general questions. So without any more words from me, we'd love to hear from Dr. Monroe. Okay.
I'm going to try to be very brief. I don't need that, no. So as an academic that's trying to recover from the academy and making a foray into the business world, I do travel the world quite a bit, and in fact, I'm on the board of the IQC up in Waterloo, Canada, a group at Tsinghua University in China, and also one of the UK hub systems. So I'm pretty well versed in at least what's going on scientifically across the world, and I'm asked very many questions from researchers in this field at these places. One of them is, maybe it's rather obvious, but one of them has to do with why the culture in the U.S. of business. That is, businesses are allowed to fail in the U.S., and then they get up and they get funded again. There's a venture capital community that understands this. They make long-term bets, even longer term than some of our science agencies, and they understand that most of these bets will fail. And in Europe in particular, there's not that culture. If your business fails, that's pretty much it. It's like getting an F on an exam or something. I think that's one interesting avenue that's playing out right now, especially as big and small companies in the U.S. Really push on this field. The other interesting thing I'll note, and this concerns maybe more the governments in the Pacific Rim, there's wonderful work going on at SK Telecom, and we've heard of what's going to happen soon in Hefei, China, and Japan we haven't heard much about, and Singapore has a real outsized presence in this field. And those places are very interesting. I was in Seoul for the first time 2 years ago, and the business climate in those countries has, and again, I'm not a politician, you guys know more than me about this, but the economies over there, the countries and the businesses are synonymous. You've heard of Japan Inc. So there's an advantage to that. If there's a cause for the government to do something, and government is business, I'm being a little facetious there, they can do things very fast. They can have a business posture in a field that needs a business posture. I think in the U.S. we don't have that. The business is, I would argue, rightly divorced from government. And fortunately, business is starting to play in this field. I will note before sitting down that it was just announced this morning that next Tuesday the House Science Committee will have a hearing on a national quantum initiative that they're considering. Maybe it's part of a bill, maybe not. But the big challenge in the field now, as I see it, this is maybe, I shouldn't bring this up, this has to do with the National Quantum Initiative, is that industry doesn't really have a great cadre of engineers that grew up on quantum, that are comfortable with quantum bits and so forth. Industry has great engineers, but they're great engineers with classical computing. In 1950, when we were transitioning from vacuum tubes to transistors, it wasn't the vacuum tube engineers that thought of very large-scale integration and scaling up silicon. It was a new generation of physicists and engineers. It's probably going to happen in quantum as well. But unfortunately, the quantum people still are at the universities, they're in academics, and there's sort of a middle ground, and I think the government, even in the US, can play a big role. The DoD labs, the DOE labs we heard earlier, and also labs like at NIST and so forth. So I think that's all I'll say. Thanks.
Hear me? Good. Okay, so good afternoon, everybody. It's a real pleasure to be here, and thanks very much for the introduction.
Sure.
I want to start with a disclaimer. So I'm delighted to be here talking about the international quantum race, and specifically representing Australia's part in that race. My accent, though, is from the UK, so I feel a bit of a fraud, really, but I'll do my best to represent and do justice to my Australian friends and colleagues. So we've talked a lot all morning about the quantum innovation that's underway and where that's going to take us in the coming years. I want to start by saying that we're already in a quantum world. Our knowledge of quantum mechanics has allowed us to understand the periodic table of elements, has allowed us to understand chemical reactions, has allowed us to develop the semiconductor industry. So from transistors to lasers to GPS to MRI imaging, we're actually already in a quantum world, and it's part of our everyday life. And this is what we refer to as the first quantum revolution. Now, it's really quite amazing when you think of it. On every, semiconductor chip, you're going to see billions of transistors. So in this room, there are probably maybe even trillions of transistors for all the, phones and laptops that we have with us today. And we consider this to be normal. And very soon, I think that the second quantum revolution will also be seen as normal. So what we're really focused on now is what are the next steps for the quantum technology development. We've talked about a lot of these things already this morning. It's attracted a lot of attention. It's very hard to see a day go past without seeing some kind of article on what we're doing and what the quantum computing or quantum security world will bring to us. And there's a lot of developments in the field. So we've been talking about governments investing in it, research institutions, but there are also a lot of private companies increasingly stepping up to the mark. And Australian government and Australian companies are also part of that. And they have a lot of assets which are helping Australia play what we believe is a strong role and make a strong contribution to this field. So what steps is Australia doing to really develop a quantum ecosystem? Because fundamentally, this is a new technology, it's new good quality jobs, and it's the future of our world. So Australia is really looking at it in three main ways. First of all, developing centers of excellence. So centers of excellence are really priority research institutions that are funded both from government and from private enterprise that are really focused on areas that are national priority. So this past year, the Australian Research Council inaugurated 9 new centers of excellence, and a couple of those were really focused on quantum technology. The centers of excellence together received an investment of over $250 million of Australian dollars. And what they're doing is working with research institutions, government, and private companies to develop these technologies and bring them to maturity. So some examples here, there's the Center for Quantum Computation and Communication Technology, really focused on developing a quantum computer. You have the Center for Excellence in Engineering Quantum Systems, so really focus on broader quantum technologies. And separately, the University of Technology in Sydney developed a Center for Quantum Software and Information, which, a bit like some of the work done by Q Branch, is working to develop the software that can work with some of the other developments and make us have a system that's really going to work. Because as we know, there's no point just having a quantum computer if we don't know what to use it for or how to use it. So that's one area where Australia is really moving forward. And again, that partnership with industry is very, very important. Second area is making sure you have the teams ready to do it, ready to work in the area. So fortunately, developing the centers of excellence also has the added benefit of building that new generation of engineers and scientists who are familiar with the technology and are able then to start to implement it more broadly in industry. Of course, we do need to invest more in STEM education. Most recently, the Australian government added an extra $100 million to really reinforce that the STEM education field. Australia being a much smaller country than the US, so that is quite a lot of money for Australia. And of course, as I mentioned before, partnerships with industry are really key. I've chosen to highlight one here. You have the University of New South Wales, which is working on the Quantum Computation and Communication Technology project, but they're doing it in conjunction not just with the Australian government, but with Telstra, the big telecommunications company, and with the Commonwealth Bank, the biggest Australian bank. And I do want to make a shout out to both Telstra and the Commonwealth Bank for really supporting innovation and technology in general in Australia across the board, both in quantum computing here, but also quantum cybersecurity and other areas. They're very dynamic and very interesting partners for technology. So now I'd like to change tack a little bit and talk about some of the companies that are emerging out of Australia in the quantum technology space. So I'm going to start with quantum computing innovation and talking about silicon quantum computing. So basically, as we've heard this morning, quantum computers can be based on a number of different hardware options. And the University of New South Wales, since about the year 2000, has been working on a silicon-based approach to developing qubits, headed by Professor Michelle Simmons, who's shown in the bottom here of my slide. And they've made some huge progress. In fact, I think last year they were able to build a qubit that was in stable superposition for 10 times longer than previously achieved. And that stable superposition is really important because that drives how much time that qubit will be available for computational purposes. So Silicon Quantum Computing was founded just this past August to really take that knowledge and that technology and build it into a practical quantum computer, silicon-based quantum computer, which would have 10 qubits by 2022, which is the goal. And again, a good partnership with academia and industry there. So the second company I'd like to focus on, the second area, is really in developing the quantum software piece. So Michael Brett, the CEO and founder of QBranch, was talking about this morning, and he, of course, will do it much better than I will. But what I'd like to highlight was that QBranch is really a good, shiny example of a very strong cooperation between Australia and the US on this innovative technology. So QBranch was launched by an Australian systems engineering company, which was then known as Aerospace Concepts. It is now headquartered here in DC, but a lot of its development still takes place in Adelaide, Australia, and they have other offices around the world. So again, a great collaboration and technology development activity here. So the final area I'd like to focus on is really on quantum cybersecurity. And I'm going to talk a little bit about my company, QuintessenceLabs, which really focuses on that as well. So as we've heard throughout the day, quantum technology is a double-edged sword. It brings a lot of promise with quantum computing and quantum sensors and quantum simulations, but it also does put the security of our data at risk. And this is where, in a way, you can have quantum can fight quantum, because quantum cybersecurity can use quantum hardware to protect from some of the attacks of quantum computers. So what QuintessenceLabs does is some of the things we've heard about today. We do classical cybersecurity. By that I mean encryption and key management. But every one of our devices goes out with a 1 gigabit true random number generator embedded, about the size of a half-size PCI card embedded in each device. So that means you never have to rely on pseudo-random numbers, and it's all you have the strongest keys behind your encryption. We're also working on quantum key distribution technologies. We've done demonstrations with Telstra, and we're currently working with the Australian DoD to bring that, to productize our current, I'd say, demonstration product, and also bring it to the next step, which is really that free stream approach, which goes beyond the fiber optic channel. So I'm going to pass over these slides because this is introducing concepts that have already been introduced in terms of QKD and true random, but just underlining they are very, very important to secure our data moving forward. So just want to end on the note that these are just examples of headlines that appeared in the past month in Australia, just underlining the interest and also the pride that people have in developing an indigenous Australian quantum technology and participating in this quantum race. Thank you very much.
Good afternoon. My name is Rene Copeland, and I'm in charge of the Dwave government subsidiary here in the Washington, D.C. area. And on behalf of Dwave, I wanted to say thanks for allowing us to speak today. I'm going to talk a little bit about Dwave, the company, and how it's trying to transition from being primarily a research organization to being a sustainable business. And in the process of doing that, we'll talk about some of our customers, in particular those international customers. Our approach to this is really to try to get our technology in front of as many smart people as possible. And I will probably not contribute to your overall knowledge of quantum physics today, even though you've had some good presentations on it. But in all of these meetings, there's always something you can take away. And what I heard this morning, interestingly enough, was quantum computing is like alcohol. It's both the creation and the solution to all of life's problems, or something like that. And if I can get it right, we'll probably talk about that one again. So thanks for that quote. With Dwave itself, we're actually a Canadian company, so I guess this is a good place to talk about things international. We act like the startup company, but we've been around for quite some time. We go back to 1999, and we were founded in British Columbia, Vancouver, by a couple of people that were wrapping up their PhD dissertations in physics. The company today has something like 200 patents because the initial founding of the company had to do with aggregating intellectual property, aggregating IP, not necessarily in creating computing. The company is composed of about 1/3 PhD physicists and mathematicians. So, as you can imagine, sometimes the water cooler conversation gets a little bit intense. And we do have customers. Our very first customer was Lockheed Martin. And Lockheed Martin bought in about 2010 with 128 qubits. And if it's not obvious, I wanted to say specifically that the qubit count as proclaimed by D-Wave can sometimes get up to be some pretty reasonable numbers, but it's not quite the same as the circuit model or the gate model qubit count that you might hear a bit about. So IBM is doing something like 5 or maybe up to 19 a little bit later on. You shouldn't try to compare that qubit count with the adiabatic approach that we're using. The second customer was Google. Google put up the money, and the machine is actually housed at the NASA Ames Research Center in Mountain View, California. It was around 500 qubits when Google became a customer. The next customer was Los Alamos, and they bought about 2 years ago, and they bought it at around 1,000 qubits. The machine is housed one level below their massive exascale system. That was followed by Temporal Defense Systems, and TDS is really an integrator. The end customer is a classified customer here in the DC area. And that system has been ordered, but it has not been installed and will be installed sometime, probably right around the beginning of next year. And those represent the actual systems installations. The next one is Oak Ridge National Lab. And unlike the others who had put systems on their site, Oak Ridge is actually buying what they call qubits in the cloud. The system is actually housed up in Canada. We're running it for them, or part of the system for them, and they're using it remotely. So you start to see the beginnings of this sort of a cloud application of quantum computing. About a year ago, we decided that the government was going to be a big part of what the opportunity was in the U.S. So we formed the D-Wave government subsidiary, and we were fortunate to get a really stellar group of advisors or people to be on that board of directors to help us separate from the Canadian parent so that we could pursue U.S. government business. Some of them you may know, such as Jeff Harris, the board chairman, who at one point was Assistant Secretary of the Air Force and actually ran the NRO. Don Kerr also had run the NRO and had also run Los Alamos National Laboratory. He's currently vice chairman of MITRE. Fran Fleisch, number 3 at the NSA for many, many years. A really stellar board of advisors and directors that will hopefully help us pursue some of the business that we're looking for. So if you haven't seen the D-Wave, that's a picture of our lab up in Canada, kind of a large black box. And if you were to well, actually looking at the front of that large black box, you see 3 computer racks, and they're pretty much standard racks. The one on the left contains a lot of networking gear. The others just contain control and monitoring information and a bit of the gases that are used to actually cool the system. If you open the system up, that large black box, you'd see something that looked like this after you took off a cylinder that actually is surrounding that large, what looks like an icicle hanging down. The chip itself is about the size of my thumbnail. So everything you're seeing really is there to provide the right environment for that chip. And that environment is a very cold environment. We operate right around almost absolute zero, 20 millikelvin. And as you can see, we take it down in stages to get to that very cold temperature. Nitrogen gets us down to about 77. And then we use a combination of helium-3, helium-4 to get down to the lower temperatures. I think outer space is somewhere around 3 Kelvin, so it's really, really a cold environment. The shielding, that black box, shields it from the Earth's magnetic field. It runs in a vacuum, has to be on a low vibration floor. It only takes about 25 kilowatts or less of actual power. And that 25 kilowatts is not devoted to the chip itself. It's devoted to the pumps and auxiliary equipment that actually keep it cold. And that's been a constant number as we've gone from 128 to 512 to 1,000 to 2,000 qubits. The power consumption has not varied at all. And in an age where the exascale people are starting to look at something like 20 megawatts as the actual envelope for the systems that they're going to be fielding, 25 kilowatts seems pretty small. It's about half of a normal high-performance computing rack, and there's probably more power consumed in this room. The company was created, or the system was created, to solve these kinds of problems. It's not intended to solve every kind of problem. We're probably best at optimization. We're starting to do a lot of work on machine learning, and very recently, some work in material science is starting to materialize. So I think 1955 was mentioned in conjunction with a Cadillac earlier this morning. Our view of where quantum computing is probably right around 1955. You're still in the vacuum tube era, or the paper tape era, or the punch tape era, or the punch card era. You don't have compilers. You don't have really good applications. You don't have tools. But maybe you can kind of look forward and see that there might be some real utility with this thing that's starting to occupy, floors of buildings. There are more than one type of quantum computing in the market currently, and our particular type is called annealing, but there are others. And you see a lot about this gate model, the circuit model, and people like IBM and Intel and Google are taking that approach. Google, even though they're a customer of ours, is still looking at developing their own quantum computer. I think they actually have two development efforts going on, one for the gate model and one for an adiabatic model. Another model is the topological model, and this is being done by Microsoft. And Microsoft is hiring some really, really good people. I think they've housed it down in Southern California. The guy that did the Xbox for Microsoft is going to be the one that heads up the project. And the last I read, they still needed a particle to be discovered to be able to implement topological computing. So the non-abelian anion needs to be discovered, and there's some doubt about its existence. But you've got to, I think, applaud Microsoft for spending that kind of money and making that kind of bet on something that could take perhaps 20 years or longer to materialize. We think the time frame for the gate model with Google and IBM is probably more in the 5 to 10 year range. And our version, annealing, is here today, but again, it's not intended to solve all problems for everyone. So explaining what we do, we use this mountain range, and apologies to any true physicists in the audience, but these mountains are up in Montana. My boss actually lives near there. They're the Beartooth Mountains, and use them to, it was some of our trainings to try to explain what the computer does, and it's really kind of the optimization explanation. But if you're looking for the lowest point in that mountain range, presumably that lowest point is the solution to some sort of an optimization problem. If you're a classical system, in some fashion, you'll traverse the mountains, looking at each point, making a decision in terms of which direction you're going, et cetera. Try not to get caught in a local minima, and you'll eventually get to the lowest point. If you're using an annealing technique, the mountain range really represents your problem. And about 10,000 times a second, the machine will simply collapse to that lowest point or lowest points, probably, and you can read out the solution to your problem. The difficulty is casting your problem into what looks like a set of mountains, and we are still working toward producing tools that will make that easier for customers to do. It matters because we've been hearing a lot about Moore's Law. Everyone's predicting the end of it. There's a guy at Microsoft that's actually created a law about Moore's Law, and he claims the number of people predicting the end of Moore's Law is doubling every couple of years. So, and it's likely that one way or another, we can't continue to rely upon, Intel generating 2x the performance every, 18 months or so. Those things are getting awfully hot, and the line widths are getting awfully small. So the end of Moore's Law, we get asked to speak on this often, the CMOS, beyond CMOS, and Moore's Law 2.0 kinds of things. So we do think in one way or another it is starting to wind down. Why it matters is that right now you can't really point to a valid application in which the quantum machine is really generating better performance than classical machines. But we're coming close in some cases on toy problems and on contrived problems. Occasionally, someone like Google will deliberately create a problem that's really favorable for the annealing approach that we use. And if you think about that mountain range, they'll create really, really tall, steep mountains and really, really deep valleys. And we'll benchmark against some of the internal systems that they have. And they did this back in December of 2015, and they got a result that was something like 100 million times faster than one core of a classical system. But the problem was very contrived. It was very synthetic. It was only a single core. But it did give them hope that, they were perhaps on the right path to do something. But we do think we're starting to get to that point where we're crossing over now and can maybe see a time when quantum systems will actually start to hold their place against some of the classical systems that are out there. In terms of investment around the world, this is a chart from the UK from 2016. And you can see that for the most part, most of the normal places are starting to make the right kinds of investment, and this is for all of quantum information science. Now, most of D-Wave in the field is a product of the supercomputing industry, or the high-performance computing industry. And that industry is fascinated with this top 500 business that they look at every 6 months. And they rank all the computers in the world, the top 500. And particular attention is given to the top 10. And they use a code called LINPACK to do this ranking. LINPACK is, everyone will concede, doesn't really measure anything that's particularly useful, but it's the only one that's been around for 30 years or so it continues to be used. And Jack Dungera down at the University of Tennessee cranks this out at each of the supercomputing conferences. So I went back 10 years and looked at where we stood in 2007 on this top 500. And you can see that the U.S. occupied the top 8 positions, with 2 positions going to the Europeans, and a variety of U.S. companies, Cray, IBM, even Dell had a ranking in that. And then I looked at what we did last June on the 2017 top 500, and the U.S. is now down to number 4, and it has actually, I think, 5 positions, although the slide says 4, with Japan occupying 2, China occupying 2, and Switzerland occupying 1. So a big shift in terms of where we've been in terms of the top 10 of the top 500 classical compute systems in the world. But if you added up number 1 and 2, then it's expressed in petaflops. The summation of 1 and 2 is much greater than numbers 3 through 10. So these are very, very powerful machines that are coming out of China now. And I believe that they're not necessarily using Intel chips for their processors. Some of them are developed. And if you looked at the entire top 500, we're about half and half relative to what's going on with China. And if you fast forwarded to today, I think you saw this slide earlier this morning, there's been about a $10 or $11 billion investment in this research facility. And it's making claims to being able to break RSA encryption and demonstrate quantum supremacy, et cetera. So hopefully this will spur some of the organizations and governments around the world to start to make reasonable and comparable and aggressive investments in quantum computing. What's going on with us? Overseas, Yulik, which is a research organization in Germany, has been a prospect for a couple of years. They're still trying to get the German government in some form to fund what they're doing. But they did put together what they call quantum technology readiness levels. And as you would expect, because we've been around for a while, we got a reasonably high rating among what they're doing. This is on their website, and if you're interested in looking at what goes into it, I think number 9 actually represents quantum superiority over something classical. So this is an example of what a European customer is doing. If you look at what the U.S. is doing, Los Alamos has had a system for a couple of years. They've run a couple of what they call rapid response projects. There are 22 of them listed there. Most of them are in optimization. Some are in machine learning. There are a lot of physicists at Los Alamos that are trying to understand what's going on in the quantum world, and the D-Wave is a good machine for doing that sort of thing. And there's one down at the bottom that says other good ideas. So they're continuing to do this every year and getting some really, really good results. And it's on their website if you're interested in looking at it. This is a listing of the projects. And the one on the right, third from the bottom, says something like using the D-Wave 2X to explore the formation of global terrorist networks. And I only point that one out because it's just something we would not have done. It's something that it would really took a customer that was interested in doing this to take a look at. So the notion of getting this technology in front of people, I think is a very, very powerful one. It distilled into a graph problem. He got a reasonable result. And he said that at the end of it, some doubt about whether it would scale, would take more work, et cetera. But it's the kind of thing you would normally see in one of these. You've seen these slides before from the Office of Science. They have made these awards. There are 4 of them that are out there now. We were really glad to see that Barbara Helland and company were doing that sort of thing. We haven't talked much about factorization, which is behind a lot of the code breaking. I just wanted to say that D-Wave per se is not spending hardly any time on trying to factor large numbers. It's just not on our radar. It's not something we think that we're going to be very good at. When I joined the company, we were doing maybe 32,000 as the largest number. I think we're up to maybe a couple of 100,000 now with some different techniques. This probably will not scale, and I don't think you'll ever run Shor's algorithm on the current D-Wave. So it's not a priority for us, although some of our customers are starting to look at it. Volkswagen. again, had been a prospect for a couple of years while they're waiting to get their funding together. They started to use the system. They took a bunch of data from Google, and this represents traffic flow from the Beijing airport to the airport. And they were trying to optimize the taxis actually in the traffic flow. So using the D-Wave, they were able to do it. And the graph on the right, that's the heat map where the congestion occurs. You can see on the right that the heat map doesn't represent any congestion. It looks like they optimized to reduce congestion, but didn't necessarily optimize to reduce distance or fuel consumption or something like that. But it's an interesting problem. It's also one you can actually talk about to your, to your mother or to your wife or spouse or something, as opposed to some of the physics problems that we get. This one is on portfolio optimization. Faisal Khan at Abu Dhabi and the Abu Dhabi Stock Exchange with someone from Oak Ridge, and one of the guys I work with just took a simple portfolio of about 200 stocks and tried to do portfolio optimization. First time it had been tried, got a reasonable result. We've encouraged them that if they start to get really, really good results, to make sure that they give us a call before they publish the paper. Harold Treese at Virginia Tech University. Harold had worked at Los Alamos many years ago, then also up at P&L. He attended a training class we had maybe 3.5, 4 years ago. And then we didn't see him for about 2 years. And the next time we saw him, he's still at Virginia Tech, but he now has a company called Data Fission. And Data Fission is a company that's formed that's trying to recognize objects in 4K video streams. So he would film Frisbee playing on the university quad and be able to pick out the people, pick out the Frisbees, et cetera. He also was able to do things like take a picture of a known terrorist and run it through Google and through Bing, and he shows the results you get here, and then he shows the results that he got with his Data Fission effort. Harold has since sold his company to Oracle, and he's disappeared again. I'm sure we'll see him in a couple of years. But they're interested in it, not at all for the, the government IC aspects of it, but more interested for having to do with searching databases. And there's also a connection to Sony, so perhaps searching film databases. But it's an example of someone with no particular training taking a class, going away and thinking about the problem. And the technique he used was a traveling salesman technique, which is just one we use for training. What we're doing, this could be our version of Moore's Law. Every couple of years, we try to double the qubit count. Starting around 128, we actually started shipping systems, but there's some pretty long times in between, coming from a few qubits to coming to a pretty large number of qubits. We're currently up to about 2048 is the current qubit count. However, as with most vendors, there's another system, and if you were to sign on to the D-Wave and try to do some programming, one of the things you'd see would be the graph on the left, which is actually the qubits in kind of a graph representation form, the dots being qubits and the lines being the connections between the qubits. So about 2,000 qubits, about 6,000 connections, by no means sparse. The graph on the right represents the next generation system. About 5,000 qubits, about 25 to 35,000 connections between the qubit. A little hard to get your head around exactly what's going on there, but much greater connectivity, and hopefully we'll be able to solve some additional types of problems. Our software environment is as bad as our programming model. It's a very difficult one, but I show this because of two things. One is at the very bottom you see the chip. We're discovering that we can actually write to something called the QUBO, this quadratic unconstrained binary optimization. And if you can get your problem in QUBO form, you can then get it into the chip. So a lot of work is being done to get problems into that form, both here and overseas. And one of the things we've done is with this code called QBSolve, which allows you to run problems that are actually greater than the size of the chip, partitioning it, if you will. Not a performance increase, but certainly a size increase. And also the left side, a lot of the activity is coming from some of our customers. The Lanel Assembler from Los Alamos, Jade from Oak Ridge, 1Qubit has done some libraries up in Vancouver. There's something called Q-Tip that was coming out of Europe. So it's starting to become a much more full ecosystem. Programming classes, there's one going on this week in Finland, oddly enough. A week ago, there was one at University of Memphis down in Tennessee with the FedEx people. Before that, we're at the Canadian, CDL, the Canadian Destruction Laboratory in Toronto. Before that, down at Oak Ridge. So We run these pretty consistently at customer locations. We've done them for many, many locations in this area. We do open classes. The next one is coming up sometime in December if you're interested. We now have a user group, and you just missed the user group meeting, which was about 3 weeks ago. It was down at National Harbor. It was the second one where we bring in customers from around the world. And this last one had a really, really large international representation, particularly from Japan and from Korea. And if you're interested in any of the projects from Los Alamos or from the presentations from the user groups, they're all available, and you'll be just amazed at the wealth of areas that people are starting to explore with quantum computing, particularly some of the stuff that's now coming out of Europe. So, thank you.
Hello again. So I've been asked to talk about the effort that Canada is putting into quantum technology. So hopefully I'll be able to convince you today that Canada is more than a land of hockey and donuts, but we have a very strong presence in the quantum sphere. So Canada, as a country, was one of the first nations to do strategic and massive investment in quantum technologies. So we have hubs, several hubs that are quite sizable, all across the country, from Vancouver, Calgary, Toronto, Montreal, Sherbrooke, Ottawa. But the anchor of the Canadian effort actually happens in the region of Waterloo, which is about 90 miles west of Toronto. And this is what I'm going to be talking about today. It's what we know, it's what we call the Quantum Valley. So the philosophy behind the Quantum Valley, or the vision behind it, is that yes, we've heard a lot about quantum computing today, and we've heard about quantum key distribution, and we've heard about post-quantum cryptography, but the superseding subject is quantum information, the idea of using qubits to do things. Quantum information gives us a platform to build new types of technology. And what we're trying to do in Quantum Valley is to seize the full opportunity of what quantum information can give us, from computing to sensing to materials to information security. So we want to sort of create a full ecosystem that will be able to adapt and also leverage all the opportunity that quantum information will offer us in the future. So to do this, we sort of created a full ecosystem to ease from the research all the way to the collaboration to be that transition as smooth as possible. And with the ultimate goal of creating a quantum industry in Canada. So there's several players, and I'm going to sort of speak about each of them, but everything is happening within a radius of about 5 kilometers or 3.5 miles. So it all started with about 15 years ago, where we created a public-private partnership to create a very strong and broad research base to look at what quantum can do for us. And then in the past 5 years or so, there's been more and more, as the technology and the science evolved toward more commercially viable product, we've seen private investments spark a series of programs that sort of transition from a research and laboratory device to something that goes in the marketplace and solves some problems in the industry. So one of the key players in the Quantum Valley is Perimeter Institute. So Perimeter Institute for Theoretical Physics, it's a think tank about theoretical physics. They're looking at the big questions in the universe, things we don't know. They're looking at, how the universe works. And sort of their motto goes something like, today's theoretical physics is tomorrow's technology. I mean, if you look in the past, all the technologies we have today are deeply rooted in just us asking, hey, how does thing work? How does these things work, and how does physics work? And then several years later, sometimes centuries later, some great technologies came out of this. The Institute for Quantum Computing, which is where I work, is based at the University of Waterloo. So it's an academic research, but it has a very broad and market-facing research agenda. So from asking the question, for looking at the fundamental question about the limits and the capabilities of quantum information, quantum computing, and all those things, all the way down to commercializing some of the technologies. Despite the name of IQC, we're much broader than just computing. Again, I mentioned quantum computing is one aspect of what quantum information can do. So our goal was to create a broad and wide breadth research base so that we're able to navigate through all the new discoveries. Because now we know that quantum information can have a tremendous impact in computing, communication, for sensing, materials. Well, the truth of the matter is we're just starting to investigate the power of quantum. So by establishing a broad, strong research base, it allows us to adapt as the field moves forward and as new applications are found. So these are the four main research areas that we have. And so there's some long-term, there's some short-term. But again, our goal is to build an industry, a quantum industry in Canada. And then there are some of the technologies that are a bit more short-term, like quantum sensors. Quantum sensors, for example, are being used today for material science, for imaging, even for cancer detection, even for oil exploration. So these are technologies that started in labs but are currently being transitioned toward the private space. At the moment, IQC is about a community of 200 researchers, roughly 28 faculty members, 40 postdocs, and 125 graduate students. And we have room to grow. We're going to grow by about 35 to 40% in the next 5 to 10 years, 5 to 7 years. And also, in addition to world-class talent and world-class research, we believe that quantum technologies will spurt out the lab by having world-class facilities. So for the past 15 years, we've been putting a lot of effort and investment in the Waterloo region to build facilities to allow us to develop those technologies, from a 10,000 square feet class 100 clean room to ultra-quiet labs for doing quantum metrology, to like this machine, for example, here, which is a very unique deposition system for quantum materials. And quantum materials will play a very important role in developing and getting quantum devices into the market, because it will allow us to study new phenomena, create new devices that won't need large dilution fridge or a large magnet, and be allowed to go from laboratory setting into more of a consumer setting type of thing. Also, with all this, with all the research, IQC is very focused on training the next generation of scientists, engineers, and leaders. I think both Chris and Jane mentioned that if we want to move toward a quantum future, we need our engineers and our scientists to not only understand, but be able to apply ideas of quantum information. And we need a business leader to be able to also foresee what are the applications for their own business. So in the recent years, we've seen a lot of the technology moving closer and closer to market. So in the region, we've established a series of programs to transition this, to make the transition from research into the private industry as smooth as possible. So a couple of the examples is, at IQC, there's the program called the Transformative Quantum Technologies, which is a research accelerator that has 3 grand challenges. One of them is to build a quantum computer that will show quantum supremacy, so something around 50 to 100 quantum bits. Another one is to demonstrate large-scale distance quantum key distribution via satellite. And then the third one is to develop useful quantum sensors. And as part of this grand challenge is also an early adopter program where we want to partner with industry, where they might not be fully knowledgeable about what quantum can do, but they have problems and they're trying to find some solution and want to get together and see how we can collaborate with the industry. Another example is the Quantum Valley Ideas Lab, which is a not-for-profit sort of pre-incubator that is highly, highly focused on a few specific technologies that have demonstrated science. So we're past the research part, we're past the proof of principle, and now they're looking at bringing that into the market. And it's very focused on useful, high-impact quantum technologies. There's also Quantum Valley Investment, which is a private venture capital fund of $100 million that's specifically focused on commercializing quantum technology. And the newest addition is the Lazaridis Institute for Economics and Management, which has a goal to train the new the people for the management of disruptive technologies, and quantum technologies being one of them. So all in all, in the Waterloo region, there has been in the last 15 years about $1.6 billion of investment, both from the private, government, philanthropic, and different funding agencies for research. And I'd like to finish by saying that although we're creating this full ecosystem in Waterloo and we're trying to build an industry around the region of Waterloo, collaboration is extremely important. Like, we cannot do it alone. And then if we want the science and the technology to move forward, collaboration across the globe has to happen. So we're partnering with universities and industry all around the world to get to this sort of quantum future as quick as we can. So thank you very much.
Up to some questions. Real quickly, though, I'm going to claim my privilege as moderator to ask the first question, and it's going to be a lightning round kind of a question. I'm putting you all on the spot. I want you to be very, very, and you'll see why some of you are particularly put on the spot with regard to this. And that is that if you could, and I'm anticipating to a degree what we're going to be talking about in the next panel, but if you could think of the way in which the United States government, which just happens to be headquartered right here in Washington, D.C., the most important ways in which, the single most important way in which it could play a key role in helping to develop and extend the kinds of quantum research and quantum technologies that are already underway in your own companies, in your own, in Quantum Valley, or also too for the U.S. quantum industry, what would be the one single focus? And here I'm thinking about international cooperation, obviously, as well as from the point of view of a national initiative.
Lower the bar for IP law, allowing industry to work with academics and government. It's such an early stage. You could make the case that early use IP is for the good of everybody, including business. That's a complex beast. I know a little bit about it, and probably won't happen. But I think in order to have an innovative hub, for instance, maybe a military lab or some type of hybrid between industry and academics, to have embedded engineers that work for Boeing or work for Lockheed and so forth. The IP is continuously the problem there.
And how would for the benefit of our audience, how would early use IP work ideally?
Well, there is a model that I don't totally subscribe to this at this early stage, but the Semitech model of semiconductors, where the companies back, I don't know when this was, probably the 70s, they realized, okay, it's going to be silicon. We're going to build computers out of silicon. We need standards. It's better for everybody if we just forget about our IP and just collaborate on a standard. And the government funded this, and the industry benefited, society benefited. It was a big deal. Now, the difference, of course, is that we all knew there were silicon transistors on the way, and right now there's a handful of different technologies, and it's not clear that we need a standard just yet. But this could come in a number of years.
Yep.
So I was actually going to talk about the need for certain standards in certain areas, such as the random number piece. So if there are ways to help accelerate the move towards some standards, I know ETSI's working on some telecommunication, NIST is working on some. At least for, say, the random number standards, that's been in process for a while. And why not also think about what standards should there be to validate a QKD system, for example? So I think that should also be explored. That would be helpful. At the moment, people, when they're buying something, they don't know if it's the right, if it meets a certain level of performance.
Just basically trying to provide budgets to fund the acquisition of more systems. And right now, the DOE has been able to put together a couple of acquisitions, but they did it very difficultly. They had to find these budgets, create these budgets. They really weren't budgets that are sustainable and ongoing. So they're still working to try to make that happen. Two, I think, much like you'll probably hear in your next panel, there's probably a need for something similar to the exascale program, but to focus that on quantum computing, where there's an acknowledgement that it takes a lot of influx of government money to be able to get to the point where the U.S. might actually have an opportunity to eclipse what's going on now in Asia. So I would say primarily dollar-based, primarily budget-based activities.
Martin?
Well, as academics, I will say more money. So it always helps. No, but I mean, in the United States, there's always been a lot of investment being done in quantum information and quantum computing. And I think if there's a presence of a bit more program, like Chris Monroe mentioned this morning, like DARPA and IARPA, which are very targeted, where they say, okay, here's the milestone you need to hit in the next 5 years. So that could really help push forward a typical type or certain type of technology. But what I see, let's say from where I'm from in Waterloo in the Quantum Valley, is there seems to be lacking in the United States sort of a full ecosystem to build an industry around those things. All right? So there's lots of investment at the university level. And then also there's several companies that started down in the valley, like Rigetti is an example, where so they get some VC funding, but they are the only quantum computing player there. So they do their things and they do great things, but there's not the whole ecosystem around them. I think this is something missing sort of in the United States. There's not one place where you can find the research institutes, the VCs, the path to commercialization type of thing.
And that kind of proximity is important for innovation.
Yeah, I think so.
It's a key element. The other thing I'll point to about the DARPA, IARPA model as a way to go about this is that I think what you also need for effective government funding is permission to fail. And one of the advantages of both DARPA and DIARPA is they know that the funding that goes out to the various projects, that most of them are never going to see the light of day. And you have to be willing to accept that risk, that some of your money is going to go down the drain, but you're also going to have big winners at the end.
And we need to realize that pretty much anything right now in the quantum technology, because it's so early in the game, everything is high risk, high reward. Yep. So high risk means failure is part of the game.
Yep. We'll talk more about it again, too. I'm looking forward to it at the next panel. Questions here? Yes, there is a mic, and you'll want to be able to speak into it and identify yourself, etc. Please.
I'm Mitzi Wertheim with the Naval Postgraduate School, but I was trained as a social anthropologist. However, I was at the beginning of IT at the Defense Department, and I created the Energy Conversation, which got energy as a topic we could talk about in Washington. I have two suggestions. One is you need to get stories bringing together the ideas that we've heard out today in newspapers and magazines all over the country. This is a topic that a small number of experts in the country understand and the rest of us don't. So if you want to get public support for providing money for this kind of institution, you need to inform us. Listening to your story, I thought about how California needs to use your tool to figure out where to place recharging electric cars, because they've now decided, I think they have to have electric cars in 5 years or something, and the question is, anyway, I'm giving you a suggestion. Okay. But how do we get the stories out? Are you willing to collaborate? Are you willing to go to the big magazines and say, we'll tell you how to write it?
That's happening already. I mean, just yesterday or 2 days ago, there was a big Wall Street Journal story about Google and quantum supremacy. This morning, I saw on the archive that the IBM group showed that 49 qubits is not enough. I mean, it
has to get down to not the intelligent, but people who don't have a lot of time to learn about it. I mean, you really do. We have on both coasts the elite, but this vast country doesn't have people who are necessarily interested in these kinds of things. So all I'm suggesting is explaining it to people in a hurry. That's the Tyson term for.
The field is full of hype, and I worry that it will just get even more hypey. I mean, there is a lot of press out there. I mean, every week there's something.
If you're looking for it.
Question there?
I'm Catherine with the U.S.-China Economic and Security Review Commission. So I'm just wondering, we're talking about the international race. So how does China fit within this race? And do you see it as moving farther ahead in certain fields? And how does it compare to where your country is leading?
Well, if you look at what's been the various story that we've heard in the past couple months, so I think it's fair to say that right now China, when it comes to quantum communication and long-distance QKD, they're quite far ahead. I mean, they put massive investment. They have a lot of highly educated people, many people working on this. Where they stand on quantum computing, I'm not entirely sure. I know they're working on it, but don't forget, they announced just a couple days ago a $10 billion program. So it'll be quite interesting to see. But from my perspective, one thing that I find very interesting with the way China invests is that at the core of the government money, it says you need to collaborate internationally. So it's not really an us versus them. It's like we're all in this together. Yeah, we all want to have a piece of it, of course. But it's not like they're doing things in secret or anything. Like they're fairly open. Like they're experimenting with the satellite. As part of the collaboration, they are collaborating with Anton Zenninger's group in Vienna, and then they're going to build a ground station in Singapore. I think one in Russia, and one is somewhere else. It's just
yeah, but we know where the $1 billion came from to launch that rocket. I think the one thing in this field that's capital intensive. In Australia, they have a wonderful effort in silicon, as Jane told us, to make perfectly silicon 28 crystals, no isotope 29 in there. That's super expensive. It may cost $50 billion to get enough of that. In my field, lasers have to be made that are engineered so well. It costs billions to do this. Any technology, superconducting technology, if it costs $10 billion, China will just do it without asking, and they'll put an army together to do it. This is interesting. I don't think any other government in the world is able to throw together something fast. This $10 billion institute, it's going to take 2 years for them to put it up or something.
Absurd like that. Yeah.
It's incredible.
And I guess I would add, since I put up the chart about classical computers and what they did with the top 500 and the top 10, is that at one point the U.S. was on a path to do this exascale project, this 10 to the 18th flops per second. But now it's generally conceded that China will be the first one to reach an exascale. It may not be a useful exaflop in terms of what they're doing, but the general feeling is that they'll get there before us. And if you switch to quantum, the chart I showed about the cooling of the D-Wave, those units are called pulse tube dilution refrigerators, and there are about 2 companies in the world who make them, and they're both in Europe, one in Finland and one in the UK. And we watch them pretty closely because it's kind of a key component of what we do. And over the last year, their numbers have gone up tremendously in terms of the numbers that they're making, but virtually all of them are going into to Asia. So we're really expecting that China will probably, if they choose to, do something pretty interesting with quantum computing, at least the version that we're doing, and likely with the gate model as well.
I would say that it's going to be very hard to match what China is doing, but maybe one of the silver linings for some of the international researchers is I've heard some of them say it's easier for them to now find funding for their projects, albeit at a much more modest level. And to your point, this is a story that might actually gain some broader understanding of what the potential of this technology can be.
To answer your question about where China is with this, the last report that I heard is that they are now working on a 20 qubit computer. That's their next goal. But the point is, that's some distance from that quantum supremacy threshold. But they are focused on that threshold. And that center is going to be working tirelessly and intensively in order to achieve that. And I think the big difference from the point of view of U.S. versus China on these things is that the Chinese are thinking about quantum information technology. They're thinking about it strategically. And we don't yet. And that's a gap that I feel needs to be closed. But I don't want to anticipate the panel next. Got time for one more question, and then we're going to transition to our next and last. Go ahead. Microphone on the way.
I'm just curious. I heard today that we have a lot of progress in quantum computing, but there's also a proposed standard that computers need to be encryption. Let's put it that way. Need to be quantum computer safe. So I see a race here between one and the other. Can you comment on that? I mean, what happens if we have progress in one area but not the other?
I think the context of quantum computer safe had to do more with decryption, a very narrow, and as Aaron put it, the last application of quantum computers. I think it's much more exciting, the opportunities for not being quantum computer safe, but being able to do things, being able to find out where to put all the charging stations for the cars in California. Logistic problems. These are wide-ranging, and I think the quantum computer safe aspect is one narrow aspect.
And also, it's been mentioned a few times, what we refer to as a cryptographic relevant quantum computer. This is way down the road. We're talking millions and millions of quantum bits. Now, that doesn't mean that you shouldn't care about it. The threat is there, and we need to make sure to address it. But when you look at the potential solution, like either post-quantum cryptography or QKD, those are significantly well advanced, and they wouldn't necessarily call them fully viable just yet, but close enough. But the chances of seeing a full-scale quantum computer that can break cryptography in the next 10 years is, I would say, the risks are fairly low, but the risks are still high enough to say that we should not ignore that threat, and this is an important thing.
I would add that the U.S. government long ago didn't fund very aggressively quantum key distribution using post-quantum techniques, and the reason is the human factor. If the plain text exists before you encode it, that's where you get it. You look behind their back, and I was told by folks in the intelligence community that they're not so concerned.
Well, let's thank our panel for. And then we should take a 5-minute break? No.